Hi everyone. So welcome to my video on sigma notation in the Mathematics Essential series. Sigma, often called summation as well. So summation, getting used to Surface Pen. Sorry, that excuse is going to wear out, isn't it? Sigma notation. Okay. Well, what is it? It usually has the following form. I'm actually having problems with my Surface Pen being buggy, so I have to make sure the rest of my hand stays off the screen for it to write. So maybe I can lean on that excuse for a while. But anyways, so its form is typically like this. So you have this symbol here, which is the ancient Greek capital letter sigma. Okay, sigma. Again, what you've got is a lower bound. So lower bound and an upper bound. Okay, and then here you have an expression. All right, and typically sigma notation is used as a shorthand way of writing the sum of the terms of a sequence. Okay, so if you've got a long sum, rather than write out all of the terms, you'll just use sigma notation to write it in a compact notation. All right, so it'll probably be easier to, rather than go through anything formal, just go through some examples. Okay, so more mathematically, the form is going to look like this. Some variable which starts at some number, often it's 1 or 0, and we just have some variable for the upper bound. Okay, so one example is going to be the sum. This is how you would say this: the sum from I equals 1 to 5 of I. Okay, so in this example, our expression is just I. Our lower bound is 1, and our upper bound is 5. All right, and then we could go and expand this sum, and we're going to get whatever I starts at, and in this case, it starts at 1. Now, I is going to increase by 1 with each term, so that in the second term, I is going to equal 2. And in the third term, I is going to equal 3, and so on. And we would stop when we got to the upper bound. So this fifth and final term is when I ends up equaling 5. Okay, so I starts at the lower bound of 1, and you have as many terms until you get to the upper bound where I equals 5. Okay, and then you could go and simplify that expanded sum. Okay, here's another example. Okay, the sum from j equals 2. Okay, you can really use any variable for the lower bound. That's called a dummy variable. I might say a bit more on that later. So the sum from j equals 2 to 50, our lower bound is 2, our upper bound is 50, and our expression is, let's say, 3 plus j squared. So I won't write out all the terms of this sequence, but this is a good example for showing what sigma notation or summation notation is useful for. So we have 3 plus j squared. It's going to start at 2, and we're going to have like 48 terms. So rather than wanting to write all of that out, you just write it in sigma notation. But if we were to expand it, and I want to expand it fully, it would start like this. So the first term would be 3 plus whatever j starts at squared, and j starts at 2. So 3 plus 2 squared. Okay, plus, okay, then we're going to have 3 plus 3 squared, because j equals 3 in the second term. Okay, plus, and so on. So the next one would be 3 plus 4 squared, until we would get to 3 plus 49 squared. And then our last term would be 3 plus 50 squared. And then if you really wanted to, you could crunch all that arithmetic and simplify it, and you just have one big real number, really. So big real number, really. Just have one big real number. Now, this is something that's handy to know. So the variable in the lower bound, and usually in the expression, is called a dummy variable, because it doesn't matter what you choose. Okay, so for I, the sum from I equals 1 to 10 of I squared. So let's say our expression is I squared. Some bugginess with the pen. Hope it goes away. Would really just be equal to the sum from j equals 1, if we picked another variable, to 10 of j squared. Okay, so another way to think of this being, to make sense of this term dummy variable, is that there's really no meaning attached to I, or that serves any different purpose than j does on the right hand side. other than just being like a hook to hang numbers on. Okay, it's really just a placeholder. It's not like, for instance, if we're talking about functions where we say y equals some function of x. Okay, and then typically the meaning attached to something like this is that we'd have a function which would graph. Okay, and for each input value into the function, which is for each x value, there's going to be a corresponding output value, which is the y values, and then you'd think of the vertical axis as being the y-axis, and the horizontal axis as being the x-axis, and you can't just interchange x and y. Swapping them would make a difference, or using them interchangeably wouldn't go down well. That's another way of thinking of the term dummy variable is the opposite of this. Okay, so there's no special meaning attached to I or J. If you're familiar with complex numbers or imaginary numbers, the I there is not I squared equal to -1 or anything like that. Yeah, it's not the I in imaginary numbers. Okay, no meaning attached to I and J. They're just little hooks to hang numbers on. Okay, now this is also important to note is that the same sum, when we write it in sigma notation, could be written in slightly different ways. Okay, so you could see two different sums written in sigma notation, written differently, but they actually are the same sum. So here's an example of that. So let's say we have the sum from I equals 1, so our lower bound is 1, and our upper bound is 10, of 2i plus 1. Okay? Well, this is actually the same sum as this. The sum from I equals 2 to 11. So our lower bound is 2, our upper bound is 11, and one expression we could use is 2i minus 1. Okay, and I'll just expand out some terms to show that these really are, well, I mean, it's not a proof, but to kind of just, like check some values and see that they correspond. So let's do a few terms of the sum. Actually, I'll just write out the whole thing. So this would equal, okay, 2 times 1 plus 1, okay, plus 2 times 2 plus 1, plus 2 times 3 plus 1, plus 2 times 4 plus 1, plus 2 times 5 plus 1, plus 2 times 6 plus 1, plus 2 times 7 plus 1, plus 2 times 8 plus 1, plus 2 times 9 plus 1. If anyone has ever had this kind of problem with their Surface Pen and has found a fix in OneNote, I'd love to hear it. Sometimes I go to write and nothing comes up. I have to sort of stroke the screen several times before the pen writes. Now remember, our upper bound was 10, so we started at I equals 1 and we are continuing until I equals 10. So our final term would be plus 2 times 10 plus 1. Okay, and if we simplified, okay, our first term would equal 3 plus, okay, our next term would be 5. Okay, the next term would be 7. All right, the next term would be 9. The next term, and you can see that all we are getting is the odd numbers starting at 3 until we get to 19. So all of the odd numbers from 3 to 19. Okay, so the next one, 2 times 5 plus 1 is going to be 11. All right, plus 13 plus 15 plus 17 plus 19, all the way up to 21. I looked at this term and thought it was the final one. I forgot about this one. Okay, and then we'd have plus 21, 2 times 10 plus 1. Okay, now, if we expand this one, we are going to get the same thing. All right, so I'll rewrite it. We have the sum from, was it I equals 2? Yes, I equals 2 to 11. I equals 2 to 11. Not writing, there we go. And with my goldfish memory, I think I was 2i minus 1, which was our expression for calculating each term. Come on, right? 2 times I minus 1. Yep, 2i minus 1. Okay, and you would see that we would just get, the first term would be 2 times 2 minus 1, which would give us 3. The second term, actually write them out so you get, get a feel for sigma notation. Okay, 2 times 2 minus 1 plus 2 times 3 minus 1 plus 2 times 4 minus 1 plus, and I won't do all of them, but the final term is going to be 2 times 11 minus 1. Okay, and you would see that this would just be, well, the first term would be 3. Okay, that's 2 times 2 minus 1 plus 2 times 3 is 6 minus 1 is 7. Okay. Sorry, 2 times 3 is 6 minus 1 is 5. 2 times 4 is 8 minus 1 is 7. Okay, and then so just continue for a bunch of odd integers or odd natural numbers, and we'd end up with 2 times 11, which gives us 22, minus 1 would give us 21. No need for bracket. Okay, and you can see that's what our final term was, and we got 3 to begin with, and I'm sure you trust me about the ones in the middle. Okay, so both of these sums here really expand to the same thing. They just give us all of the odd integers from 3 to 21 inclusive, or the odd natural numbers from 3 to 21 inclusive. So yeah, the way that a sum is expressed in sigma notation is not unique. Okay, other expressions can be the same sum. Okay, I'll just do examples for the rest of the video. So perhaps I'll do 3 examples of expanding sigma notation, and then I'll do 3 examples of taking a sum, so taking a sum that's already expanded like this, and coming up with ways of writing them in sigma notation, because it's important to be able to go back and forth, okay, between expanding and contracting. Sip of coffee. Okay, so here's an example. Sum from I equals 3 to 7 of x raised to the power of I. So this would equal x to some power, I, but it starts at 3, so it'd be x cubed, plus x to the 4th, plus x to the 5th, plus x to the 6th power, plus x raised to the 7th power. And now we've arrived at I equals 7. We've reached our upper bound, so we would stop. Another example, let's say the sum from j equals 1 to, so let's throw a curveball into n. How would you express this? Well, I'll give you the expression first. Let's say of negative 1 raised to the power of j. Okay, so this power is going to be part of what changes? Of a sub j. Okay, so we're going to have these a terms that are being subscripted by our dummy variable j. Well, maybe you can pause the video and think about what this might look like. But it's going to look like this. So negative 1 raised to the first power, so we don't really need to write that. I'll write it anyways, just to show the form, times a sub 1. Okay, plus negative 1 raised to the second power times a sub 2. Okay, the thing that might be confusing here is that our upper bound is just n. Okay, so it's like, how do we know when to stop if we don't know what n is? Well, we stop at n. And that means writing something like this. Negative 1 raised to the third power, so that would be the start of our third term, times a sub 3 plus, you don't know how long n is, so you just write a little ellipsis here to say this is just going to keep going until we get to negative 1 raised to the nth power times a sub n. You even might do something like this. Notice that the second last term would be this, negative 1 to the power of n minus 1, okay, because the second last term would be right before n, so it would just be 1 less than n, so you could express it as n minus 1, okay, times a sub whatever number comes before n, which all we can do is express as n minus 1. Okay, and then you'd have your final term, which is negative 1 to the n times a to the n. Now we could have just as well as expressed it like this, because maybe n is 2, so maybe we're not really going to have a third term or a fourth term or anything like that. But negative 1 raised to the first power times a sub 1 plus, put a little ellipse in between, -1 raised to the n. We're going to have to write the n minus 1th term, and in this case, we're not, times a to the n. Okay, that would be fine. I'll point out something about this -1 raised to the j factor in front of the a sub j. So I'll point out something about this, is that you see, if we were to simplify, notice that when -1 is raised to the first power here, okay, it's just going to stay -1. So we're going to get -a sub 1. It would simplify to that. Okay, our second term, okay, here, notice that the -1 is being squared in our second term. So we are just going to get, it's going to disappear. Just -1 times -1 would just be 1. So you'd just be left with 1 times a sub 2. So you just write plus a sub 2. But then when you get to the third term, the same thing happens as with the first term. Okay, because you can have a negative times a negative times a negative again. Okay, so the product of 3 negatives is going to be negative. So you're just going to have -a3. So you would write minus a3. And this is what we call oscillation. So notice that the sign of the terms are just oscillating. So whenever you raise -1 to a power, and that power in a sum is just going to change. Say it starts at 1, becomes 2 in the next term, becomes 3 in the next term, and so on, all the way up to the nth term. For odd powers, -1 will just be -1, but for even powers, -1 squared is going to become +1. Okay, so the first term has an odd power, so it's -a1. Second term has an odd power, so it's positive a2, and it's -a3. And we know that the fourth term would be plus a sub 4. We have minus a sub 5 because -1 would be raised to the fifth power, and so on. But we wouldn't know what to say about -1 raised to the nth power because we don't know whether n is even or odd. So we would just have to say this. Okay, we would just have to say -1 raised to the nth power. If we knew that n was odd, then we could say minus a sub n. If we knew that n was even, then we could just say plus a sub n, but we don't know. So we just have to write the -1 raised to the nth power times a sub n. Okay, let's move on to another example before I start doing examples of how to go back in the other direction. So how to go from an expanded sum into sigma notation. In other words, how to look at something like this and know how to express it, perhaps as this. Nope, that should be a j. Okay. So basically how to go back in the other direction. So this will be the last one for expanding. So let's say we have the sum from I equals 1 to 4. So our lower bound is 1, our upper bound is 4. Now this one might be tricky too. Our expression is just 3. Okay, maybe we can put it in brackets, doesn't really make a difference. What do we do there? Because I doesn't appear. So I'll put a question to you. Would this just equal 3? That's strange. It seems like we should have more terms than that because it seems like we need to get up to the term where I equals 4. What does I equal in the first term? Well, it would be 1, and in the second term it would be 2, but it's not really clear how to use I here. Well, actually, what this would equal is, and I should say it is clear. I'm just saying, it might throw you if you haven't seen something like this before, where the dummy variable just doesn't appear anywhere in the expression. Okay, well, it is there. It is in the expression because you can just think of it as this. The sum from I equals 1 to 4 of 3 plus 0 times I. Okay, so it is kind of there in the background. It's just implicit. Okay, so what this would equal is 3 plus 3 plus 3 plus 3. Okay, because you can think of I playing a role like this. The first term is 3 plus 0 times I, or 0 times 1, because I equals 1 in the first term, plus second term would be 3 plus 0 times 2, and so on all the way up until we got to, I'll just actually write it, 3 plus 0 times 3, plus, and our final term would be 3 plus 0 times 4. So in each case, it's just 3 plus 0. Come on, surface pen. Yeah, each term would just simplify to 3 plus 0 plus 3 plus 0. And you can see like the zeros aren't contributing to the sum. So we're really just left with 3 plus 3 plus 3 plus 3. Okay, so let's do some examples now of going back in the other direction. So let's say we had 6 plus 8 plus 10 plus 12 plus 14 plus 16. And let's say you are asked to write this in sigma notation. Well, typically you've got to look for some pattern between all of the numbers. And sometimes you can just read off a pattern. Sometimes you need to play around with the terms to see what the pattern might be. So one thing we can observe about all of the numbers is that they're all even. And even numbers are all multiples of 2. So all of the even numbers are 2 times something. Okay, so 2 is 2 times 1, 4 is 2 times 2, okay, 6 is 2 times 4. So we could think of this as being like, come on, pen, 2 times 3 plus 2 times 4 plus 2 times 5, and so on. And what would 16 be? That would be 2 times 8. Okay, so we have a common factor of 2 in all of the terms, and what seems to be changing with each term is just the number that's being multiplied by 2. So that's a good indication that the number that's changing by 1 in each successive term is the one that we should make a dummy variable. Okay, so let's express this in sigma notation. We would have the sum, again, we want these numbers to be the one that the dummy variable comes to equal, which means in the first term, what does that number start at? It starts at 3. So that means we should start with our dummy variable, I'll just pick I, starting at 3. So in other words, we should pick 3 as our lower bound. Okay, so the sum from I equals 3, that's our lower bound, to 8 is our upper bound. And it would be, the expression would be 2 times I. Okay, and you can see that if you expanded that out, your first term would be 2 times 3. Okay, your second term would be 2 times 4. Okay, then I would become 5, you'd have 2 times 5. I would equal 6, you'd have 2 times 6, and so on, until you got to I equals 8, and you'd have 2 times 8, and you'd get the same sum. All right, let's do one that's perhaps a bit more tricky. Let's imagine our sum is 1 minus 4 plus 9, okay, minus 16 plus 25 minus 36, maybe you're detecting a pattern here, plus 49 minus 64. Okay, so what observations can we make? Well, the signs of the terms are oscillating. So it starts off positive in the first term, okay, negative in the second term, and it just keeps changing until we get to the last term, which is negative. So the sign oscillates back and forth between positive and negative. And we have seen that before in an earlier example where we had something like this, negative 1 raised to the j, okay, and if the power j was odd, we'd be left with negative 1, and if it was even, we'd be left with positive 1, and that would get us that oscillation of the terms. So that's an indicator that we need to include something of this form in our expression when we write it in sigma notation. What other things in common can we notice between these numbers? Well, they're all square numbers. So for example, 4 is just 2 squared, okay? So I'll write that. 4 is just 2 squared. 9 is just 3 squared. The pen is buggy. Okay, 16 is just 4 squared. Okay, so 25 is just 5 squared, and so on. And 64 is just 8 squared. So we can see that the base, which is being squared, is changing by 1 with each successive term. Okay, so with 2, 3, 4, 5, and so on all the way up to 8. So now we've got 2 clues. And that the second clue is that we should choose in our expression the base of a square to be our dummy variable. So let's go ahead and have a crack. Okay, and notice that 1 is a square number because 1 is just 1 squared. Okay, so one way to express this would just be, let's say the sum from, I'll write it in blue, the sum from, let's pick j for our dummy variable, j equals 1 to 8. Now, we needed that oscillation, didn't we? Okay, there's a number of ways we might write this. Okay, maybe I'll show you a few ways to write this in sigma notation. But we know that we're going to need -1. Now, would we want -1 raised to the jth power? Well, consider what the first term would be. The first term would be -1 raised to the first power, and that would just give us -1. So that means our first term would be negative. But you can see here that our first term isn't negative, it's positive. Okay, so we would want the power of -1 in the first term to end up being even, so that we could guarantee that we would get +1 instead of -1. We don't want that in our first term. Okay, we want that in the second term, in the third term, in the fifth term, and so on. Okay, so what we might do to ensure that we're going to get +1 out of the first term is when we raise it to a power, since we know that the first term will be j equals 1, and that's an odd power to raise -1 to, we will just either, actually I'll go back to blue, we would just either add 1 to it or subtract 1 to it. And in this case, we should subtract 1 to get what we want. So we'll raise it to the power of j minus 1, right? And then we need the base of the number being squared. So now we would just have j, not I, j squared. Okay, so let's see if I didn't mess this up. All right, so the first term would get us -1 and to the power of j minus 1, and j equals 1 in the first term, so we would have 1 minus 1, which is going to get us 0 in the power, and then we would have times 1 squared plus -1 times, well, j would equal 2, so we'd have 2 minus 1, okay, and times j squared, but j equals 2, or 2 squared, plus I'll do one more term before I throw in the ellipse and write the final term, -1 raised to the j minus 1, but j is 3 now, times j squared, which would be 3 squared, okay, plus ellipse, because we are lazy. Oh, actually, I shouldn't throw you in with my lot. I'm lazy. And our final term would be plus -1 raised to the j minus 1th power, but j would be 8 here, so we'd be left with 8 minus 1 in the power, and that guarantees that our final term is negative, which is what we want, because our final term is -64, times j squared, j is 8, okay, and then, if we simplified this, well, -1 raised to the power of 1 minus 1, that would be -1 raised to the power of 0, and anything raised to the power of 0 is 1, so really, there's no need to write it, okay, that gets killed off. We actually know that any -1 that's raised to an even power is going to get killed off, so, we could just ignore that one, because that's going to be -1 to the 3 minus 1, which is -1 squared, which is just going to be 1, so we don't really have to worry about any of the -1s raised to an even power, because they won't contribute anything, they'll just become factors of 1. Okay, so our first term is just going to be 1 squared, which is 1, plus -1 raised to the 2 minus 1, which is just -1 raised to the first power, so it's going to stay negative. Okay, times 2 squared, which is 4. Okay, plus, we can forget about that -1 squared, plus 3 squared, which is going to be 9. Okay, and then the next term is going to be a minus. Okay, and we'd get 16, but we'll throw in this ellipse, and then we'll do the second last term. Okay, because one way we could have written this was plus -1 raised to the, well, in the second last term, j would equal 8, so we'd have the 7 minus 1th power. So we would have raised to this power, which will end up being the 6th power, times j squared, no need for the brackets really, and j equals 7 in the second last term, so times 7 squared, plus, okay, you don't have to write the second last term, but I will, times -1 to the 8 minus 1th power, times 8 squared. Okay, so picking up where we left off. Okay, so 1 minus 4 plus 9 minus something, which carries on for a while, and then we'd get up to plus. Okay, we know that this one's going to be even. Okay, the sign of the second last term will be even because it will be -1 raised to the 6th power, and 6 is an even power. Okay, so we'd just be left with 7 squared, which is 49. Plus, okay, -1 to the 7th power, 7 is odd, so it's going to be, so it's going to be negative, I was going to say odd, it's going to be -8 squared, which is 64. And you can see that we'd get the same sum. Now, I might write this another way. Okay, notice that this would also work, okay, if we went from I equals 2 to 9. So our lower bound is 2 and our upper bound is 9. Dummy variable I, expression, well, -1 to the I times I minus 1 squared. This would also work. Let's just see what some of the terms look like. Okay, negative 1 squared times, because I starts at 2, so I'd have 2 minus 1, and I won't write it all out now. I'll just simplify a bit as I go. So 2 minus 1 is just going to be 1 squared, okay, which we wouldn't write. So we can just go on to the next term, and that's going to be plus I cubed times 3 minus 1 squared plus negative 1 raised to the 4th power times 4 minus 1 squared, and so on. This time I'll write the second last term. That would be negative 1 to the 8th times 8 minus 1 squared, plus, in the final term is just going to be negative 1 to the 9th power times, come on pen, 9 minus 1 all squared. And notice that, look, you get your negative 1 squared for the first term, which would just give you 1. Okay, this is meant to be negative 1. Okay, negative 1 cubed, so it's going to be minus something. 3 minus 1 is 2 squared, you get 4. Plus, okay, negative 1's raised to an even power, so we can forget about it. And we've got 4 minus 1 is 3, squared gives us 9. Okay, minus, let's put in our ellipse. Okay, then we get to the second last term. Okay, negative 1 to the 8th is positive. 8 minus 1 is going to be 7. Then you square it, you're going to get 49. Again, we can see that we would get the same thing. In the last term, negative 1 is raised to an odd power, which is 9. So you're going to have a negative sign in front of whatever 9 minus 1 squared happens to be, which is 64. Okay, so you can see that these two are equal. Okay, so that's just another way of writing that sum. I'll do one last example before I wrap up the video. So this one's also about taking the sum that's already expanded and writing it in sigma notation. So let's take this example. So we have x squared plus 2x to the 4th plus 3x to the 6th plus 4x to the 8th plus 5x to the 10th. I actually don't know off the top of my head how I'm going to write this, but we'll, in sigma notation, but we'll play around with it. Plus 7x to the 14th, and hopefully I won't embarrass myself. But notice that we could think of this as, and I'll write this in another color. How's gray come up on this? Yeah, not too bad. Might make it a bit bigger. Okay, that's all right. We can think of there being coefficients. Well, there are coefficients in front of all of them, but just imagine that there's like a 1 there. Okay, kind of like gray. Looks like a pencil. So yeah, we can think of this as 1 times x squared plus 2 times, so this would just be exactly the same, x to the 4th. Just putting that 1 in front of the x squared term. And sometimes it's helpful to write things out in a way that's like not simplified. Okay, so often if you simplify, it makes it harder to see what the pattern is when you want to write something in summation notation. So let's imagine this 1 times x raised to the power of, let's say, 2 times 1, okay, plus what we'd have here, 1 plus 1 in brackets. So this is what I mean by writing the terms in a way that aren't simplified in order to reveal what the pattern is. Okay, times x raised to the power of, well, this time the power is 4, but we could write that as 2 times 2. Okay, plus 1 plus 1 plus 1. So you can see that the coefficients in front of the x's are increasing by 1 each time. So that's obviously going to be I. So that in our expression, when we write it in sigma notation, we will have a coefficient of I, or whatever dummy variable we choose, in front of the x terms, and then times x raised to the power of 2 times something that's increasing by 1 every time. So raised to the power of 8. So this is raised to the power of 2 times 4. So this means that we're going to have something like this as our expression. So I times x, because the coefficients are increasing by 1 every time. Okay. 7x to the 2 times 7. Okay, and the powers are multiples of 2, where the multiples are starting at 1 and increasing all the way up until 7. So our power would be like 2 times I, just picking I to be our dummy variable. Okay, so that's what our expression would be. Yeah, that's what our expression would be. Okay, so we'd have the sum from I equals 1 to 7. So I would start at 1, okay, and it would end up being 7. So upper bound is 7. Okay, so that was the third example. And just to recap everything, okay, so this is typically the form here. So you're going to have a lower bound and upper bound, okay, that's written below and above the ancient Greek letter sigma, okay, followed by an expression, okay, that will usually have the dummy variable in it, but it need not always have the dummy variable in it, okay, and, more mathematically without, writing lower bound and upper bound and expression, it's typically going to have this form here with some expression that usually refers to the dummy variable, but it doesn't have to. We saw an example where it didn't. Okay, so it's just a more compact way of writing long sums. We did 3 examples of expanding a sum written in sigma notation. Then we observed the fact that the expression of a sum in sigma notation is not unique. Okay, so 2 sums that have, where the bounds are different and the expressions are different could really just be the same sum. Okay, so there's not just one way to express every sum in sigma notation. Okay, and we also observed, so these were just 2 examples of expanding. This here referred to the fact that the variable that we use for the lower bound, so I starting at some number or j starting at some number, is just a dummy variable. Okay, so these are really equal. Okay, they're not they're not unequal just because one uses I as its dummy variable and the other uses j. Okay, and after doing some examples of expanding sums that might seem like they look different when written in sigma notation and actually come down to the same sum, we did some more examples where it got a little bit trickier because we had an x variable, we had an a with a subscript and an upper bound, which we didn't know, we just denoted by n. And we touched on a few ways that we might write it, noting that the second last term would be the n minus 1th term, and that the last term would be the nth term. So it really didn't matter that we didn't know the value of the upper bound. It was just enough to denote it by n or k or m or whatever else. Okay, we took a look at this example here where the dummy variable just didn't appear anywhere in the expression. Okay, well, it doesn't appear, but it is really there. Okay, and we observed that this really just came down to writing 3 times 4, or 3 plus 3 plus 3 plus 3. Okay, and then we did some examples of going back the other way. So we started with a sum that was already expanded. We played around with it to try and see what pattern there was between all the terms, so what properties the individual terms might share in common, and that's a good heuristic, a good way to find clues about how you might write it in sigma notation. Okay, this example here gave us a little handy trick, which is this, for how to achieve that that oscillation between signs, between terms. So when you want your terms to oscillate between being positive and negative, you take a -1 and you raise it to something. And whenever it's raised to an even power, you're going to get +1. Whenever it's raised to an odd power, you're going to get -1. Okay, and there were 2 different ways of writing this. These sums expressed in sigma notation came down to the same thing, which was just the square numbers from 1 to 64 inclusive with oscillating signs, starting at positive and ending up at negative. Okay, and then we took this, which we, you'll, if you don't recognize already, as a degree 14 polynomial with real coefficients. We looked at how we might express this in sigma notation, and that one ended up being not too tricky. Okay, so that caps off my video on sigma notation. I hope you found it helpful. If you did, give it a like. Feel free to share the video and subscribe if you'd like to see more. The next video, I think, will be on surds. Yeah, so stay tuned for that if you want to explore surds. Bye for now.